Hello dear students, in today's lecture we will try to understand some photochemistry about the Earth's ionosphere. So far in our discussions we have covered everything related to the structure, basic features of ionosphere and more importantly the variability of ionosphere. What are the factors which will influence variations in terms of number of electron density or the factors which can influence the appearance or disappearance of ionospheric layers during the daytime and nighttime. In continuation, in this class, we will look at each of these ionospheric layers, for example, D, E, F1 and F2. We will try to see what are the major chemical processes or photochemical processes which happen in those respective layers and what are the ions or types of ions which will be dominant in these regions. So, going back, we have already done this simple calculation where we can calculate the time constant that it requires for the recombination to happen or for the removal of electrons and ions from the ionosphere, which is dependent on the type of process like radiative recombination and dissociative recombination. So, we realize that the radiative recombination is a very slow process and the dissociative recombination is very fast, which means dissociative recombination can take care of all the ions and the electrons in a very short period of time, right. So, the occurrence of radiative recombination or the prolonged duration of radiative recombination is what is responsible for the ionospheric layers, some of the ionospheric layers to persist during the night time, right. Now, let us look at each of these layers and try to grasp the basic features of these layers, because this is very important. Not everything, not all the layers are same, not all the layers witness the same photochemistry, right. So, to begin with D region. So, for all practical purposes we can remember the bottommost ionospheric layer is D region and it extends between 50 and 90 kilometers. So, 50 to 90 kilometers is the D region and this is the lowest ionospheric region. The ionization in this altitude region is by the means of Lyman alpha radiation centered at around 121.6 nanometer, ionizing the nitric oxide. Okay. So, basic ions that can be found are something related to the nitric oxide. It is weakly ionized, that means the total electron density that you can find in this region is not much. It can vary up to 10 to the power of 10, starting from 10 to the power of 8 up to 10 to the power of 10 during the daytime. Okay. So, depending on the time of the day, the electron density may vary. So, mid afternoon the electron density will be highest, right. And at night when there is no direct sunlight, when there is little sun incident radiation except for the cosmic rays, the D layer almost disappears except at very high latitudes. Okay. So, in the figure what you see is this black box is the region which is highlighted as the D layer or D region of the Earth's ionosphere, and D layer is the bottommost layer. So, something that you should remember is the altitude limit within which this layer will exist and the typical order of electron densities 10 to the power of 8 to 10 to the power of 10 and then the wavelength which is majorly responsible for the formation of D layer, right. Moving ahead, some more interesting aspects about the D layer. The electron densities in the D layer normally does not have a distinct peak. This is clearly visible even from here also. It is like a continuum, but a small change in the slope. So, this is what you are calling as the D layer. So, it is not like a F2 layer which has a distinct peak like this. This is a 250 to 300 kilometers, where the electron density or the number of electrons per unit volume is increasing to the highest value and thereafter it is decreasing, right. It is not like that. So, D layer does not have a distinct electron density peak. Okay. And the ion production and the recombination processes are highly complicated between 50 to 95 kilometers. Why are they complicated? Because it is a lower atmosphere. Considering the total altitude that we are talking about, it is like bottommost layer where the densities are reasonably high. So, the production and the recombination processes are are not very straightforward or not very simple. I mean, not there are many processes. That's what I actually wanted to say. The hydrogen Lyman alpha, H alpha, at 121.6 nanometers, it's a very strong spectral line in the sense its intensity is very high. So, it can penetrate to almost up to the D layer. So, if the intensity is low, then you know that as it is traveling into the optically thick medium, its intensity will decay at an exponential rate. So, effectively the distance over which this radiation can ionize will be small, right. Contrary to that, if the intensity is very high, everything goes opposite to what we have just described. Okay. So, this has enough energy to ionize nitric oxide molecule, which is found in very small amounts. Okay. So, because nitric oxide, if you go back to the thermal distribution of atmosphere, thermal characterization of atmosphere, in which we have realized how does the layer exist. So, we know that certain point of altitude, because of the radiative cooling processes, the temperature decreases with respect to height, right. So, this opposite trend is because of this molecule's ability to effectively radiate energy into the space. So, this hydrogen Lyman alpha penetrating into the bottommost ionosphere between 50 to 95 kilometers can ionize nitric oxide, which is also not a major species. Nitric oxide is a trace species, very small amounts of nitric oxide, let us say in ppm, exist in the upper atmosphere. So, this production generally dominates from 70 to 95 kilometers. So, broadly we have defined the layer to be 50 to 95, okay, and this production because of the nitric oxide generally dominates about 70 to 95 kilometers. And solar flares can be a significant source for the D layer. What does it mean? Solar flares accompany strong enhancement in the spectral intensity or spectral emission from the sun. So, you have more radiation coming from the sun. So, as a result, the more intense radiation can penetrate into much lower altitudes, thus producing significant contribution in the D layer ion densities. And the recombination processes are both height and temperature dependent. We know that because height will decide which species will be dominant at that altitude, and then the temperature dependent. So, some of these reactions, reaction rate coefficients are temperature dependent. So, you write k as a function of let us say e to the power of something or e to the power of x divided by t or something like that. That means, so the temperature will also decide the rate at which a particular chemical reaction will happen. This is very well known to us, right. So, these are the basic aspects about the D layer. So, we know where does it exist, 50 to 95 kilometers. We know what is the major ion species, nitric oxide NO plus. We know which radiation produces it, 121.6 nanometer Lyman alpha, H alpha. And then we also know that solar flares can affect the electron densities in the D layer to a significant proportion. Right. Now, moving on, the ionospheric layer which is sitting just above the D region or D layer is called as the E region. Okay. Now, why are we referring to these layers as D, E, F1 and F2? Why don't we refer them as let us say A, B, C, D, or we call it as 1, 2, 3, 4, or we could have come up with a naming system something similar to troposphere, stratosphere, something like that. No, for some reason these layers are defined as starting from D, E, F1 and F2. What happened to ABC? We don't know, right? So, try to read online, you easily get the answer. Why are we calling them as D, E, F1 and F2? But maybe I will myself explain in the following lectures, but you try to see and find out the answer why we are referring the ionospheric layers as D layer, E layer, F1 layer and F2 layer, etc. Okay, coming back. So, the ionospheric E region is sitting just above the D layer, which is between 90 to 140 kilometers. So, 50 to 90 and 90 to 140. So, this is the upper atmosphere. So, the E region is produced by X-rays. Go back to our discussion like 3 or 4 lectures before. We know that X-rays are the most intense solar radiation and they pack a lot of energy. They can dissociate molecules, they can ionize molecules, they might as well, I mean they can easily ionize atoms. So, the entire spectrum of atmospheric species, nitrogen, oxygen, molecules, atoms, other trace species, all of them can be easily ionized by the X radiation. So, E region 90 to 140 kilometers is mainly produced by X rays and far ultraviolet radiation ionizing molecular oxygen. You combine this with the understanding of how the atmospheric densities change with respect to height. So, we already know they decrease exponentially. So, in the 90 to 140 kilometers, we have more oxygen present. So, it will be ionized, producing ionizing molecular oxygen. So, X radiation is mainly responsible and FUV. So, let us say we write X-ray and far ultraviolet, which means the X radiation is able to penetrate up to almost up to 90 kilometers, starting from 500 kilometers. And typical electron densities are of the order of 10 to the power of 11 electrons per meter cube. So, in comparison to what we have seen in the D layer, the densities were 10 to the power of 8 to 10 to the power of 10 electrons per meter cube. The density maximum. So, we can define N max. N max tells you the peak electron density, and we also define another parameter which is H max, which is the height at which this peak electron density appears or can be seen, right. So, now you see something that is very important and some aspect which can lead to the discussion of Chapman's theory starts to appear here. So, the ionospheric densities are continuously changing with respect to height, and they seem to peak at 4 different altitudes, and we define these altitudes, the layers, as the ionospheric regions, right. Now, why is it like the ionospheric layers are reaching a maximum value and thereafter they are decreasing? This simple idea or this relation is established by the Chapman's theory, which gives a mathematical description to the ionospheric layers or their shape, like reaching a maximum value and thereafter decreasing, right. Because this is not straightforward. We are not getting an exponential decay, we are not getting an exponential growth. We are getting something, a mixture of these two things, right. So, from here onwards, we will define N max, which is the electron density maximum, and H max, which is the height at which this maximum electron density will be found, right. Now, for the case of D layer, the electron density maximum was varying between 10 to the power of 8 to 10 to the power of 10, and then H max was not clearly defined. So, in the last slide itself, the electron density in the D layer normally does not have a distinct peak, right, but in E layer we have a distinct peak at around 100 kilometers. Okay. And at the night, during the night, E layer begins to disappear due to the lack of incident radiation, and this result in the height of maximum density increasing, right. So, D layer begins to disappear. In the bottommost part, it of course disappear, but here you see this figure, electron density on a logarithmic plot on the x axis and the altitude on the y axis. The black, the box is the E layer, right. So, it has a distinct peak at 100 kilometers, and during the night time, its strength, the strength of E layer significantly decreases, which is also seen from this figure. So, daytime is given by daytime is given by the solid lines, and the nighttime is given by the dashed lines, right. So, daytime solar maximum is given by the red solid line, and nighttime solar maximum is given by the red dashed line. Okay. So, here you see D layer has completely disappeared. There is no D layer here, but there is D layer here. E layer of course is present with a much larger intensity within solar maximum itself. E layer is of course there, but the strength has decreased by several orders of magnitude. Okay. Why? Why? Because there is no direct ionization happening, right. So, only the recombination processes are there, and even these recombination processes are not completely dissociative recombination process. So, there is radiative recombination, that is why the process is taking some time, and as a result E layer appears with a very small intensity, but nonetheless it is there. Okay. Right. Now, some specific features about the E layer. So, E layer starts 95 to 150 kilometers. This layer is the one in closest agreements with the Chapman's description. This is important. So, Chapman description is what we are going to derive mathematically in the next few lectures. Chapman's description, what is Chapman's theory? Chapman's theory is a simple mathematical treatment which will reproduce the ionospheric layers. Okay, some analytical description of the observed ionospheric structure like a Gaussian. Okay. So, the ion production in the E layer is caused by X-rays, we have already seen 1 to 10 nanometers, okay, and far ultraviolet radiation between 100 to 150 nanometers. So, the extreme ultraviolet radiation is between 10 to 100 nanometers generally. Okay. So, 1 to 10 nanometers is highly energetic, and then ultraviolet radiation between 100 to 150 nanometers. Okay. So, the ionization is mainly because of the dissociation or because of the ionization of O2 and N2 to O2 plus and N2 plus. So, what type of ions are these? These are molecular ions. So, because the energy is very high, it can directly ionize these molecules. So, among these, N2 will disappear very quickly by charge exchange because of the availability of oxygen or whatever. So, N2 plus will quickly disappear by charge exchange. So, see here the charge is being exchanged onto oxygen, and here nitric oxide molecule is forming with a ionized state and atomic nitrogen. So, that O2 plus and N2 plus are the dominant ions, and recombination is generally by dissociative recombination. Right. Now, basic features, what are the basic features? E layer stretches from 95 to 150 kilometers. This layer is very close in agreement with the Chapman's description of ionospheric layers, and it is by 1 to 10 nanometers of X radiation and 100 to 150 nanometers of far ultraviolet radiation. Ionization is mainly by O2 and N2, which will immediately exchange the charge with available oxygen, producing two different types of molecular ions, one O2 plus and another NO plus. Because there is a lot of availability of molecular ions, the recombination process is dissociative. So, dissociative recombination process will immediately remove or scavenge out the electron density. Right. Now, let us look at the continuity equation. We know what is the continuity equation. We have defined the continuity equation in a simple term. The rate of change of electron density with respect to time is equal to the rate at which the electrons are produced minus the rates at which the electrons are lost by the means of recombination process, and then you have plus minus del n E. So, production, loss and transport. Now, we will suitably modify the recombination. So, let us say we remove the transport term. So, we have already seen the loss is equal to minus alpha effective Ne. So, alpha effective is the effective recombination coefficient. Why I am calling it as effective? Because the recombination processes can be due to O2 plus or NO plus. Obviously, the recombination coefficients for these two processes are different. So, an effective recombination coefficient takes care of both these recombination coefficients. You add them in such a way that it represents the total recombination coefficients. Okay. And in addition to this, more interestingly, one more aspect about the E region in particular is that the incoming meteors, the meteors get ablated in the mesosphere, which is like 90 kilometers. They produce meteoric ions. Most important or the most dominant ion or the species in this region is sodium. So, it will produce Na plus ion, Mg plus, all these metallic ions will be produced in the E region because that is where the ablation is happening, and because of whatever the availability of photons or whatever the temperatures, etc. Because of these ions, a very dense layer of electron density can occur in the E region, and these are called as sporadic E layer. This sporadic E layer is not a regular phenomenon, it does not occur every day, it is not there every day. It can occur at some time and it may not occur. And this sporadic layer can be attributed to the meteoric ablation. Right. Now, then we move on to the ionospheric layers F1 and F2, or we combine them F1 and F2 and we call it as composite F layer. Okay. Here we have to understand both these layers independently because the photochemistry of these two layers is different. So, F1 layer is sitting immediately above the E region or E layer between 140 to 200 kilometers. Okay. The typical electron densities are 3 10 to the power of 11. So, we are moving from 10 to the power of 8 less than 10 to the power of 10 less than 10 to the power of 11, and now here is going to be less than few, let us say we call it as few as n 10 to the power of 11. Okay. So, this is the D layer and this is the E layer, and now we are talking about F1 layer. Okay. So, the typical electron densities are higher, of course, several 10 to the power of 11, and this is caused by atomic oxygen by extreme ultraviolet radiation. Now, we are talking about radiation gaps are also, we are very clearly able to see this, right. So, in the D layer, the most important radiation or the wavelength that you should remember is 121.6 rather than this H alpha, and E region it was 10 to 100 nanometers and 150 nanometers, yeah, 100 to 150, 1 to 10, okay. So, this is 1 to 10 nanometers, the X-ray 1 to 10 and X and far ultraviolet radiation. And in the F1 region, now we are talking about 10 to 100 nanometers, 10 to 100 nanometers, 10 to the power of 9 meters. This is called as extreme ultraviolet radiation. Okay. So, 1 to 10 nanometers is the X radiation. The most energetic part of the ultraviolet radiation is 10 to 100 nanometers, and 100 to 150 nanometers or up to 350 nanometers is the ultraviolet. We call it as extreme ultraviolet. We can subdivide it into another class which is XUV, okay, which is just at the boundary of X radiation and ultraviolet radiation. Then you have extreme ultraviolet radiation, then you have ultraviolet radiation, then you have far ultraviolet radiation, which almost mixes or which almost extends up to the visible radiation itself, right. Now, what is important for us? For us now it is we are moving in terms of wavelengths. So, as you see, as you are moving towards the higher altitudes, more energetic radiations are appearing. So, 10 to 100 nanometers is the radiation which is responsible for the formation of F1 layer, right. So, basically you remember the heights 50 to 90, 90 to 140, 130, 140 to 200 is the F1 layer. So, the most important ionic species is the atomic oxygen. Why atomic oxygen? Because atomic oxygen is formed in this region by the dissociation of molecular oxygen by the same ultraviolet radiation, right. And moving on, so you have this box which is representing both F1 and F2. So, F2 layer is about 200 kilometers, about 200 kilometers. So, usually this layer has the highest electron density, and this can be written as, which is going to be less than 2 10 to the power of 12. So, this is called as F2, right. So, usually has the highest electron density 2 10 to the power of 12 electrons per meter cube. So, consists primarily of ionized atomic oxygen and nitrogen. See, here there are no major molecular ions. So, the recombination processes have to be solely dependent on the availability of atomic ions, which means the radiative recombination process is the most dominant process. So, we already know very well that radiative recombination processes are slow, their reaction rate coefficients are very, very small, and which means that it is going to take a lot of time for the entire removal of charged species, which means they can exist or they can persist during the night time as well. Okay. So, consists primarily of ionized atomic oxygen and nitrogen ions. Okay. Now, these are the layers in the ionosphere. So, just for visual understanding of these layers. So, here we have the commercial jetliner which usually flies at, let us say, 10 kilometers, 10 to 12 kilometers max. And then you have the D region, and then you have a strong occurrence of electron density within the E layer. It also matches very well with the meteoric ablation height, which is the the mesosphere. And then you have F1 layer, F2 layer, and some satellites can be seen at 500 kilometers. At night time, you have only the E region which is appearing, and D region completely disappears. F1 layer completely disappears. Right. So these are some photochemical aspects about the various ionospheric layers. So in the next lecture, we will try to continue this discussion. We will learn more about the ionospheric, because the intention is that you develop a very basic, starting from a very basic to very advanced understanding in the Earth's ionospheric physics. Okay.